I want to get back into this idea of a probability distribution. And this is really where we're going to be the rest of the class. The last 4 weeks we have together. This is all we're going to be doing, is this idea. We're going to go from discrete to continuous. Right now we're dealing with discrete ones because the outcomes you're counting. This one, that one, that one, this one, that one, this one. But we'll move to continuous when we need to. And we do need to. I mean, eventually you're going to want to start talking about things like IQ scores, weights, heights, temperatures, things like that. And that's when you can't count those things. You have to measure them. So, but we'll get one thing at a time. What do you remember about these from Thursday? An acceptable answer is absolutely nothing. That's totally fine as well. You may have forgotten quite a bit. We only did one, and we did it through an experiment. So, but what comes to mind? You close your eyes, think about Thursday, which was like 3.5 months ago. What do you remember?
X and PX.
Good! And that's really the biggest thing right now, is an X column and a probability of X, P of X column. Love it! Beautiful. You remember that? I'm stoked. I'm stoked. What went here?
Random
Oh, that could make me happy.
variable values.
Yes! The values of your random variables. The random, this is supposed to be blue. The random, I think I put the wrong ink in it. The random variable values. Good, and there's no, they vary. I mean, obviously they're called variables, but sometimes they start at 0, sometimes they start at 1. The one we did on Thursday was rolling a single die, which started at 1 and went to 6, because that's the outcomes you can have for rolling a single die, 1, 2, 3, 4, 5, 6, assuming the die is a normal 6-sided die. That could change. It could start at 0. You guys brought up awesome points on Thursday last week. I forget how the near fist fight started, but people were concerned about the 1 through the 6 on the die, and somebody said, what if they were colors, which was genius, by the way. It was absolutely genius. What if they are colors? If they're colors, I would never ask you to set this kind of a table up, because it's pointless. You can't average colors. But somebody else then asked, what if there are different numbers on them? I forget who that was. It was a great question. What if it was like 2, 4, 6, 8, 10, and 12? Well, hell yeah. Then it's 2, 4, 6, 8, 10, and 12. Whatever your variables are, go here. Now, what makes them random? You don't know which one you're going to get on, exactly, they happen randomly. You don't know which one you're going to get on each throw of the die. Now apply this to your life. You don't know what's going to happen when you leave the house on your bike at 5 a.m. Sometimes you go down and hurt your rotator cuff. Sometimes you get to school in 15 minutes totally fine with no flat tires. Sometimes you get 3 flat tires. I mean, I've actually kept track, kind of informally, of the number of flat tires I've gotten per commute over the past 20 years. One day I got 3 flat tires on one commute in one 25-minute period. Now, anybody that's not completely out of their mind, after the first flat would go home, throw the bike down, get the car, and drive to work. Changed the first flat, kept going, got the second flat, realized there was a piece of glass still stuck in the damn tire that I forgot to get the first time. Then the third flat was a huge 4-inch nail that went sheesh right through the tire, ruining the tire and the tube. That was on College Way. I pushed the bike up and just got here and wished I kept whiskey in my office. But nonetheless, I can keep track of that number of flats. What's the least number of flats I can get riding to work?
0.
0. And that happens most of the time, almost every single day. I just jinx myself, of course. I'm going to get 5 on home. Exactly, knock on wood. But the idea is you can keep track of that. 0 is the least. 1, 2, 3. Technically speaking, is there a top end to that? Technically speaking, no. I can just keep getting flats. Get back on the bike, pops again. Get back on the bike, pops again. I'm going to go back a little bit, come back on the bike, pops again. I mean, so far, 3's the max I've seen. That doesn't mean you can't have more. The idea is you don't exactly know what's going to happen every single time. You get on the bike, you start riding. And somewhere between 0 and n is going to be the number of flats you get that day. And that likelihood is therefore kind of known. I know there's about a 95% chance I'm not going to get a flat tire. That means there's a 5% chance I'm going to get at least one, using the stuff from your last project. And that's kind of what this idea is too, is figuring out what these values are. And most importantly, once you have those, figuring out this. Figuring out these. Now sometimes you can figure these out via just thinking about a situation, sometimes. Sometimes you can do mathematics to figure them out, but very often you have to simulate them or look at historical facts to figure them out. For example, I just said roughly 95% of the time I don't get flats. How do I know this? I've kept track. I've kept track of my history. There's no mathematics that I can do to figure out whether I'm going to get a flat today or not. There's no mathematics at all. Once I completed the commute, I can put a little check mark and say, good, no flat today. And that goes into the realm of everything else for the past 20 years of keeping track. But sometimes you can do mathematics, sometimes you can't, but the idea is you have to measure these likelihoods. You have to measure these likelihoods somehow, whether it's experimentation, whether it's mathematical, whether it's pure history, which is looking at results and then carrying it forward. There's dangers in all of those things. Your next project, not due till next week, shows you one way of using computer simulations to get these numbers. I'm also going to do one in class today with you guys in that game called Chuck-a-Luck. Actually, we're going to do one pretty soon with 2 dice as well. But we're going to have the dice in front of us to help us understand them as well. Cool? What else do we remember from these? What's special about this column? There's a neat little mathematical, speaking of mathematics, there's a neat mathematical result.
The sum of all P of X is 100%.
Totally stoked over there, Mon. If you add up all the P of X's, you have to get 100%. Assuming you've allotted for everything properly. Assuming you've allotted everything properly, that should add up to 100%. Very, very, very nice. Very, very, very nice.
And if it doesn't, something's wrong.
Something's off, yeah. Now sometimes you can be off by, say, 100th or 1,000th of a percentage point. That's negligible. That's probably a rounding error. That happens in Excel all the time. I was in a negotiations meeting yesterday and somebody handed me a pie chart of full-time, part-time adjunct, and full-time temporary faculty. And the first thing I looked at was the pie chart was beautiful. It was a third, a sixth, and a sixth. I mean, roughly, that's what the pizza looked like. But they added up to 99.99%. I'm like, wait a minute, who are we missing? We're missing somebody who's not in. Then I realized it's just Excel. It rounded something off and it didn't quite average to 100%. That's okay. But if you're only adding up and getting 0.92, you're missing 8% somewhere, that's when you gotta start being like, something's off in there. Something's off. So 1 or 2 hundredths of a percentage point is a rounding error. Cool so far? Now, very often, once you've set this thing up, what you really want to go for is the average and the standard deviation. And one of the ideas that I had on the quiz for next week is to walk you guys through a manual calculation of an average. I made you do it last time, and I'm not sure it made a whole lot of sense last time when we actually crunched out like old school weighted means, this times this plus this times this. And watching your guys' reactions to that, I don't think it sat as well as it should have. So I had this quiz idea to do it for next week that I think will have it sit a little better. We'll rely on technology today, and we'll use the quiz to kind of get in and actually analyze each piece. It'll be written down for you. So the average and the standard deviation, the way we calculated it manually was we added up each of the random variable values times their probabilities. And we derived that formula really quickly because we knew what a weighted mean looked like, and then we adjusted it for this new distribution. Remember what we can call it now, though? We can call it mu instead of x bar. We can call this mu instead of x bar. And the reason we can call it mu, yeah, you can see that. The reason we can call it mu is because once you have the probabilities, essentially, what do you know? You know the entire, is it a sample anymore?
No. Population?
It's an entire population at that point. Once you've assigned the probabilities, you don't have to treat it as a sample anymore. It's no longer a sample, it's an entire population. Now some people will argue that the probabilities can change. True. But the more you collect, the less they're going to change, and the closer and closer they are to that true population. Essentially, the margin of error shrinks down. There's no error of the sample anymore. There still is a standard deviation. Don't confuse the fact that there still will be a standard deviation. Some folks think that because it's no longer a sample, it's a population, that there's no standard deviation. There has to be standard deviation because there has to be variance in the data. The only way you won't have a standard deviation is if, for example, every time you roll the die, you get the exact same number. So 6, 6, 6, 6. Okay, standard deviation is now 0 because everything came up 6. But you're not going to get that on these dice because there is variance in the dice. Okay? So we can now call this, remember the symbol for this little guy? Gesundheit.
Sigma.
It's that little guy, think back, that little guy, little sigma, who's tucked under S in your calculator. We'll see him again today. He's not crucially important on average in these. A way more important measure is the average because that's what happens on average. And especially as the distributions get more and more skewed, the standard deviation gets more and more inflated or deflated, depending on how you want to look at it. And it can kind of get a little bit misleading, or not even misleading, just useless. But the average is actually talking about what is going to happen on average. And by the time we get to the end of the class in the in-class quiz, you'll see how you can actually use that to your advantage in a lot of ways. Because you want to see long term. Compare and contrast this, of course, with the short term. I was talking to a student in 244 yesterday who was talking about some numbers that her doctor gave her. She had back pain and she was going for some procedures. And her doctors were giving her numbers like 70% have this and 30% have this, and she was trying to pluses and minuses of certain treatments because of side effects. You know, a side effect can be, if we get in there and operate, that something can go wrong, which is always the problem with surgery. Something can go wrong. But the idea is you have to kind of weight that. And they're going to tell you things like 70% or 30% or 50% or 45%. And you have to ask yourself, do I fit that demographic? Because what they're giving you is the average of an entire distribution. You are one data point. You are one data point. And whenever I bring that up, I want you to think about the wedding ring story I told you. I think I told you that story, right? My buddy Jim and his wedding ring.
No.
I didn't tell you this? This is the difference between believing statistics at their value and realizing sometimes how you don't apply to a statistic. So a couple years ago, my buddy Jim was taking this class with me. And it was one of those goofy fall terms when it snows in like the middle of October. And it dumps like a foot of snow and then it's gone like 10 minutes later. One of those weird, well, it wasn't 10 minutes, it was 10 days later. But it, you know, it's one of those bend October days. And it dumped a foot of snow on the campus at 3 o'clock in the afternoon. He was in OSU at the time. And he comes out and he sees his car buried under a foot of snow. And it's like that wet, crappy snow, you know, like that garbage cascade crud, they call it. So he goes out there, he doesn't have anything in the car ready for winter because it's the middle of October. He's prepping for Halloween probably. He goes out, he just starts knocking off his windshield. He has to drive back to Redmond. So he's cleaning his car off best he could, gets the roof, gets the back windshield, the tail. Gets in the car, drives back to Redmond. Halfway there, looks down at his hand, wedding ring's gone. Because assuming what happened was as he's blowing the snow off the car, the finger shrank a little tiny bit, just enough to let the wedding ring pop out, or just lubed it up enough to pop it off if it doesn't fit well. I'm sure you've had that happen to you. Maybe don't lose your wedding ring, but you understand what I'm talking about. So anyway, he calls me and he's like, John, lost my wedding ring. Dude, it's cool, it's cool. We'll figure it out. And I go out and look at the parking lot. Now by now they've plowed. So now I said these piles of stone, I'm like, we're gonna figure this out somehow. Looking around, we're gonna figure this out somehow. So then the next class, Jim brought it up in class, and I asked the class, what do you think the chances of us finding that wedding ring are? So if you had to attribute a probability to finding that wedding ring, what would you say?
99
to 1 against. So 1% chance of finding it. 1% chance. That's pretty generous compared to what some of the kids told me. Kids are saying 1 in 1,000, 1 in a million. You're not going to find it. One kid actually said, I'm not going to find it. Yeah. So that's a challenge, right? The Joe's lady, you're not going to find it.
How many people attend the school? So 1 in out of how many people?
Oh, okay. So just 1 out of 18,000-ish. Okay, good. So I took all those numbers and we averaged them, and it ended up being an average like 1 in 5,000. That was the chance, 1 in 5,000. I don't even know what that means in context of that experiment, but I know it's pretty crappy odds. But that was an average of 1 in 5,000. I said, Jim, we don't have to listen, because he was getting depressed as he heard these estimates going. I said, we don't have to listen to this, dude. We don't have to listen to this at all. So the first thing I did was I called Wade DeBrawl in IT. He's like, dude, can I borrow your metal detector? I think pretty slick. Get metal detector out there. So we walk out there, there's still about 4 inches of snow. This is a couple of days later, it's starting to melt down. And I take the metal detector, I'm like, we got this, and I put it down, and it starts crackling like, dude, how good am I? Go down, dig through, no ring. What the hell? Pick it back up. Just so you know, the dirt in Central Oregon is magnetic. Therefore, rendering metal detectors obsolete for the purposes of finding a wedding. There's iron in all the dirt. Drop a magnet in your backyard sometime, lift it up, dirt will be stuck to it. It's incredible. I lost an Allen wrench under my deck once and discovered this fact. And then I forgot it promptly when I was using the metal detector and then remembered really quickly. So metal detector's out. Without a metal detector, the only thing we can do, because the ring was platinum, it wasn't anything magnetic itself, we couldn't like run a magnet down until we found it, was just we started looking. And we'd go out and we'd check the spot. He knew where he was parked. We kind of did some amateur physics to figure out what, vector it would have taken off his hand. He was pretty pissed apparently, so he was going like this. We figured 30 feet either side. So we're out there walking around. I could tell who had been there first. Every day we'd see footprints. Sometimes I'd see his footprints before me. Sometimes he'd see mine before his. And we'd just walk around and we'd check every spot. Dig down, dig down, dig down. And then about 2 days after that, they plowed a second time.
Sweet.
Ruining all the work we had just done, rendering everything we'd done, and probably moving the ring. So back to the drawing board. 4 weeks later, I get an email from Jim. Dude, I found it. Dude, I found it. And it wasn't that far from the car. It didn't actually make it that far. It was like 25 feet away. But it had obviously been moved around based on where it ended up. It was not where it would have been originally. The plows didn't move it. But why do I tell you this story? Because just because they tell you something has a 1 in 5,000 chance of happening, you might have some control over it. That might render that number. It's like Han Solo in Star Wars. Never tell me the odds. It's that. Sometimes you have control over that. When they tell you there's a 70% chance of relapse after a certain operation, dig more. Dig more. That's an average across an entire population, not controlled for any other variables. Maybe it's different in your age group. Maybe it's different with your gender. Maybe it's different in your whatever group. I mean, there's all kinds of other variables that might not be represented well here. Patty, go!
Isn't it going up based on the amount of time you were willing to spend looking for it?
Absolutely. Every single time, it goes back to your last project. Every single time Jim or I set foot into that area to look for that ring,
Cut your odds down.
we cut our odds down of not finding it again. Because the chance of us finding it in at least one of those times goes up. As you saw, we kept planting pumpkin seeds, right?
Yeah.
We kept planting pumpkin seeds, essentially, until we finally got the damn pumpkin.
That goes with his perseverance for whatever his motivation was.
Of course.
Because he could have said, well, screw it, I'll just go buy another one.
Absolutely.
You know, whatever. I mean,
Absolutely.
and you can do that pretty much with anything, like you said, like hospital. I mean, is it really important that you care what's going to happen in surgery, or are you going to have, like, you know, this great faith in the doctor that he's going to do everything well and whatever?
Which has been demonstrated, not statistically but anecdotally, to actually have an impact.
Yeah.
Yeah, and this is, we're showing you tools here. There's some good tools we're going to be using today and also the rest of the course, but don't become a slave to them, I guess is what I'm getting at. Don't become a slave to them. There are places for them. Life insurance is a perfect place for them. Gambling is a perfect place for them. No, I'm saying that in all seriousness. Understanding gambling and how it works, it's a perfect place for these kinds of things, because the idea is they work in controlled settings, assuming these probabilities are correct. But if those probabilities can flex, that's when you have to take a step back and go, ooh, maybe this isn't science. Maybe there's something we can't measure in there.
Well, that's why they call it gambling and not winning.
Well, you can win, just not on average. And they control for that. We'll get to that today too. So first things first,